we continue with another example of a system of two equations with two variables that we want to solve. Like in the previous video, we are looking for combinations of x and y that satisfy both equations. But first we'll rewrite this in the form of a matrix multiplication. So we will write 3, 4, 2, 6 times xy is equal to 2, 1. So this is nothing other than taking this set of equations and rewriting it in the form of a matrix multiplication, where this will be our matrix A, this will be our vector x, and this will be our vector b. And the idea is that if we have ax is equal to b, we can take the inverse and multiply it on the left side and the right hand side of this equation. Times a times x is a inverse times b. This is equal to the identity matrix times x, and the identity matrix times x is the vector x itself. And if we know the inverse and we know b, we can write out the solution. Now, matrix A is equal to 3, 4, 2, 6, and this is a matrix of which we have calculated the inverse in a previous question. We know that the determinant of A is equal to 10, and so the inverse of A is equal to 1 over 10, 6, 3, minus 4, minus 2. So what we can do now is say, okay, x is equal to 1 over 10, 6 minus 4 minus 2, 3 times the vector 2, 1. Well, we can perform this multiplication, and what I like to do is multiply this matrix by this vector first and then divide the result by 10. So if we multiply this out, we get 1 over 10 times the vector 8 minus 1. So our solution is equal to 8 over 10, which is 4 over 5, and minus 1 over 10. So x, our vector x, is equal to 4/5 over minus 1/10, or put differently, x is equal to 4 over 5 and y is equal to minus 1 over 10. And this is the solution of this set of equations, and there is only a single solution. All right, so this isn't limited to two equations with two variables. You can also do this with three equations and three variables, and even with n equations with n variables. It does not work with something that is not that doesn't yield a square matrix, because a matrix has to be square for it to have an inverse, and of course the determinant has to be equal to it cannot be equal to 0. So an example of 3 by 3, 3x plus y is equal to 2, 5x plus 2y minus z is equal to 1, x plus 4y minus 2z is equal to 5. So this is our system of three equations with three variables x, y, and z, and we're looking for combinations of x, y, and z that satisfy all three equations. Now we can rewrite this as 3, 1, 0, 5, 2, minus 1, 1, 4, minus 2. So these are the coefficients. So there's a 0 times z here. 5, 2, minus 1, 5, 2, minus 1, 1, 4, minus 2, 1, 4, minus 2. So this is our matrix A. We have our vector x, y, z. And our vector B is 2, 1, 5. This will be B. Now again, we will use the same strategy here, where we want to find the inverse of A so that we can multiply this with B and find our solution. Now, finding the inverse of a 3x3 matrix is somewhat more involved, but luckily this is also a matrix of which we know what its inverse is, or at least we can calculate it. And I think this was one of the exercises we had to perform. Its determinant is equal to 9, 0, 2, minus 1, 9, minus 6, 3, 18, minus 11, and 1. So this is equal to A inverse. So we know that the solution X is equal to A inverse B. So X is equal to 1 over 9, 0, 2, minus 1, 9, minus 6, 3, 18, minus 11, 1, times the vector 2, 1, 5. And we can multiply this out again. Again, I like to multiply this matrix by this vector and leave that 1 over 9 to a later moment. So this is 1 over 9, minus 3, 27, and 30. So this vector is the multiplication of this matrix with this vector. And I can write this as minus 1 over 3, 3, and 10 over 3. Now, this is my solution X. If I want to rewrite that in coordinates X, Y, and Z, we find X is minus 1 over 3, Y is equal to 3, and Z is equal to 10 over 3. Now, remember that this is one point in 3D space, just like that this solution is one point where two lines intersect. So how do we have a graphical representation of what's happening in a 3x3 situation? And I am not very good at 3D drawing, but you have to, well, bear with me. This point is the intersection of three planes. So if we have two planes intersecting, it will be a line, and I'll make a brave attempt to draw that. So if we have one plane, and remember this extends out in all directions, we intersect that with another plane, and that intersection will be a line. And if we have another plane, say in this direction, that intersection with all those three will be a single point, and this single point in 3D space is this vector, or which has the coordinates X, Y, and Z. So it is a single solution, just like we have a single solution here, and we had a single solution in the previous example. And this is very important for the next part, is that we can calculate this this way if there is a single solution, and if there is not, and we try to use this method, strange things happen. So in practice, this is an interesting way of looking at this problem, and this is definitely one of the ways, one of the techniques that forms the basis for things like least square solutions, or solving other types of equations. This is definitely a way to do it, but there's a more general way of solving these equations for the case where we cannot use this method. And I will go into why we need a different method in the next part.